Okay, in this final lesson, we're just going to touch on the highlights of graphing trig functions. We would normally have a whole unit on this, but we're running out of time with all this NTI day stuff. But I want you to at least see the graphs so that if you have a question that appears in a future math class or on the ACT or something, then hopefully you'll have enough basics to be able to answer it. So we're going to start out with just the graph for y equals sine x. And many of you noticed the spaghetti graphs in my room. This would be where we would make that spaghetti graph. But since we don't have the ability to do that from afar, we're just going to, instead of using spaghetti to come up with our graph, we'll just make a little T-chart here and put some points. Now, if we were doing the spaghetti graph, we would measure every single radian around your unit circle. So like 0, pi over 6, pi over 4, pi over 3, pi over 2, and keep going all the way around your circle. We're just going to do increments of pi over 4 just to save a little time. But we're going to just put in for x 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. Okay, so when you find the y value, you're just going to substitute in what we have for x and then figure that out. So for example, x is 0. We want to find the sine of 0. So the sine of 0 means I would go to my unit circle, I would look at 0 radians, and what is the y coordinate? Okay, that's 0. Then at pi over 4, what is the y coordinate? And then at pi over 2, the y coordinate is 1. At 3 pi over 4, it's radical 2 over 2. At pi, it is 0 again. Then at 5 pi over 4, your y coordinate is negative radical 2 over 2. At 3 pi over 2, your y coordinate is negative 1. 7 pi over 4, it's negative radical 2 over 2. And at 2 pi, you're back at 0. Okay, so now we're going to graph what we have in our ordered pair there. Now, if you'll notice on our y's, what's the highest number? Yeah, 1, and the lowest number, negative 1. Okay, and that makes sense if you think about with our unit circle, our radius was 1, so we're not going to have anything out of that range there. Okay, then for my x's, we're going to do increments of pi over 4, so that's going to be pi over 4, pi over 2, 3 pi over 4, there's pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. Okay, so we graph 0, 0 first, and then we have pi over 4, radical 2 over 2. Now, if I put radical 2 over 2 in my calculator, what do we end up with there? Yeah, that's like 0.71. So we're going to go not quite to 1, about right there, a little over half. Pi over 2, it's at 1. And then at 3 pi over 4, you're at that same radical 2 over 2 again. Pi is 0. And then we start to go down. So it's going to be a negative 0.71. And then negative 1. And then back to that negative radical 2 over 2. And then 0. Okay. Now, this, if I connect my points here, this is what my sine graph will look like. That's actually pretty good. Probably one of the better ones I've made on this thing. I graphed these on paper a little better, but okay, so that's what the sine graph is going to look like. Now, we could go around the circle again, and if we did, what do you think will happen as we extend this graph? yeah, that pattern's just going to continue. So it's going to go up, 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 and then there. It's going to look like that. Okay. Now, this is called the sine wave, okay, because the curve makes what kind of looks like a wave. It's going to continue indefinitely, so it would continue to make a wave this way, but then also this way, because if I were to look at negative pi over 4, that's going to be the same thing as what we had at positive 7 pi over 4, so it's going to be down here at the bottom, so it would just kind of go through that point and still make a wave going towards the left. Now, a couple of key features about this. First of all, the highest point and the lowest point. Okay. If we split that difference, that has the highest points at 1 and the lowest points at -1. So if we split that difference, that gives me 1. So we're going to say this has an amplitude of 1. Okay. Then at what point does the graph start to repeat itself? Well, if I start at 0 and I trace this, once I get to 2 pi, that's when it starts to repeat. So we say from here to here, that's a wavelength. And one wavelength is 2 pi. That's also what we call the period of the graph. Okay, so period is wavelength. And that just means that after 2 pi, it just repeats that same cycle. Now, with all new graphs that we look at, we talk about the domain and we talk about the range. Okay, well, your domain, do you have a starting or ending point as you look from left to right? Okay, well, it keeps going to the left. We put that little arrow to represent that, and the same to the right. So we say our domain is -infinity to infinity. Okay, the range is talking about y. So what's our lowest y? And then our highest y. So our range is -1 to 1. Now, when we graph these, we're going to be talking about how there's this pattern with sine. And our pattern with sine, okay, if we look at one wavelength, we have an x-intercept. Then we have a maximum. Then we have an x-intercept. And then we have a minimum. And we have an x-intercept again. So we're going to focus on these 5 key points because we're not going to want to have to make a t-chart every time we graph. But by putting in those pi over 4 marks, that helped us to see that this graph is going to curve rather than just being jagged edges. But these green marks here, okay, those are our key points that we're going to graph every time we graph a sine graph. Okay, moving on to cosine. We'll make a t-chart again. Okay, and we know that our x-coordinates repeat just like our y-coordinates did, just in different spots, but the numbers themselves are the same. So when I make my cosine graph, I'm just going to key in at the quadrant angles so that I can key in on my key points. So I'm not going to worry about the pi over 4s this time, okay, when I make my t-chart. So I'm going to put in 0, and then pi over 2, pi, 3 pi over 2, and 2 pi. Okay, and like I said, we're just saving a little bit of time here by not putting in those others on the sign. We left out all the pi over 6s and the pi over 3s. But if you were to look up the sign of pi over 6, that's at a half, which would be about right there. And see, that isn't one of the points we graphed, but it does fall on the graph. Okay, well, since we since we know that the sine and cosine values repeat, we're just going to kind of take an easier route and just graph those quadrant angles instead of trying to figure out what's going to go in between, because we know it's going to curve just like the sine curve since those numbers repeat. Okay, so cosine is the x-coordinate whenever we look at our unit circle. So if I substitute 0 in for x, what is the cosine of 0? Well, when I look at 0 radians, my x-coordinate is 1. Okay, then at pi over 2, what's the cosine of pi over 2? X-coordinate there is 0. Then at pi, what is your x-coordinate? And then at 3 pi over 2, the x-coordinate. And then at 2 pi, you're back to the same place as 0, so that's also going to be 1. So when I go to make my graph this time, I have 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so those are the points I put in my t-chart, so that's what I made for my scale on my x-axis so that could match up. Now, once again, what's your highest y and your lowest y? Yeah, so we'll use the scale of 1. So now I'm going to plot my first point, 0, 1. Then I'm going to plot pi over 2, 0. And then pi negative 1, 3 pi over 2, 0, and 2 pi is 1. Now, if I were to extend this out through another cycle, what would my pattern do? It's going to keep following. So even though I don't have a t-chart for this, I can figure out what my next points are, just because this is what we call a cyclic graph, and so it repeats in cycles. So putting or connecting the points here, that's what that one looks like. Wow, that's impressive. Okay, so if I were to extend it out to the left, there at negative pi over 2, your x-coordinate is 0, so it would come down here like this, and it would just keep going to the left. So I'll put arrows there so you can see that that pattern is continuing. Okay, amplitude again. So I look at my highest point and my lowest point, okay, and I take half of the difference of that. So 1 minus negative 1 is 2, half of that is 1. So my amplitude is going to equal 1. Okay. Then for my period, I know if I start here and I trace my graph, when does it start to repeat? Right there. As soon as I hit 2 pi, it does the same thing. It goes down and up again. So from 0 to 2 pi is 1 wavelength. And remember, wavelength means period. And that distance is 2 pi. All right, then our key points again. Okay, and this is just our pattern. Every time we graph a cosine graph, we know our first point is going to be a maximum. Then I have an x-intercept. Then I have a minimum. Then I have an x-intercept. And then a maximum again. Okay, and then domain and range. Once again, you have a restriction on your domain. It goes on and on forever to the left, and then continues on and on forever to the right. So negative infinity to infinity. What about the range? Lowest point is -1, highest point is 1. You do have points there, so that's why there are brackets there. And the same thing happened for sine. You put brackets on both because there is a coordinate at graphed at -1 and at +1. Now, when I compare my cosine graphs and my sine graphs, if you're just glancing at them, do they look the same? They both make a wave. They both have a period of 2 pi. They both have an amplitude of 1. The difference is going to be here, these key points in that pattern. Okay, if you'll notice, the x-intercept are in different places for sine versus cosine. Okay, the maximums are in different places for sine versus cosine. Minimums are in different places for sine versus cosine. Okay, so realistically, you could take this cosine graph that we have here in blue, and you could write an equation for it in terms of sine, but just with a horizontal shift. So do you remember the transformations we talked about way back at the beginning of the semester, first 9 weeks? Those are going to come into play here on these trig functions as well. So that's what we're going to look at next. So if you have y equals a times the sine of bx minus c plus d, or if you have y equals a times the cosine of bx minus c plus d. Okay, what we're going to look at now, the a, b, c, and d, how do those variables affect the graph? So when you have a number in place of the a, b, c, or d, what does that do to the graph? Okay. Well, we saw when we were graphing quadratics and absolute value functions and cubic functions and logarithms and exponentials and all that stuff, that number in front that it's the graph or the equation was multiplied by was a vertical shift. Or sorry, I said that wrong. It was a vertical stretch. Okay, what's the same thing here? That a value is going to affect your vertical stretch. Well, when I look vertically now back here at this graph, that's my amplitude. So a is going to affect your amplitude. If you have a 2 in front of that sine or the cosine, instead of your maximum being at 1 and your minimum at -1, your maximum would be at 2 and then minimum at -2. So it's going to stretch that graph vertically. So first formula, we're going to say our amplitude is the absolute value of a. Now, why do I have absolute value? Okay, that's because you're talking about a distance or a length, so we just need the absolute value for that. We don't say something is a negative distance or that kind of thing. However, if you had a negative value for a, would that affect your graph? Okay, your amplitude's still going to be the same. Your maximum will be the same and your minimum will be the same, but it will flip the graph, just like normal. So it'd be reflected across the x-axis, okay? So the negative still reflects, okay, but it does not change the amplitude. So that's why the formula for amplitude has absolute value about it. All right, next is the period, and we've been talking about that as we graph sine and cosine. Period means wavelength. Okay, well, you could have a period change to where one wavelength would happen maybe instead of between 0 and 2 pi, maybe one wavelength is a length of pi or stretched out in a length of 4 pi. So our formula to find our period is going to be 2 pi over b. Okay, then our horizontal shift. That's going to be c over b. And if you remember, anytime we talked about a horizontal shift, we did opposite of the sign. Well, notice in your formula it says minus c. Okay, by using the formula c over b, then that's going to automatically mean change the sign. So that formula is the same thing that we had before. And then vertical shift, we've talked about that with every graph we've looked at. That number that's added outside of the parentheses is going to tell you how your graph shifts up or down, and it goes with the sign. So that's just D in this case. Now, we're not going to spend as much time actually physically graphing these. I set this up on MathLab to where most of the questions are just answering about what the amplitude or the period would be, or it might be like a multiple choice, which graph goes with this equation kind of thing. Okay, but I'm going to go through one graphing problem with you just so you can see how all this stuff affects the graph. So we're going to have the equation y equals 2 sine of x minus pi and actually I'm going to change this. Let's make this 1/2 x minus pi. There we go. Okay, using the formulas that we have back here, those 4 parts, the amplitude, period, horizontal, and vertical shifts, are the first thing you're going to identify anytime the problem tells you to graph. All right, and I'm just going to start abbreviating this. So amplitude is the absolute value of A. So in this case, that's a 2. The period is 2 pi over b. So 2 pi divided by, and my b is 1/2. So if I divide by 1/2, that's just like multiplying by 2. So that's going to give me 4 pi. My horizontal shift is c over b. My c is pi. My b is 1/2. Once again, we're dividing by 1/2, which is the same as multiplying by 2, so my horizontal shift is 2 pi. And then this one doesn't have a vertical shift. And we see very few with vertical shifts on your assignment, so you won't really have to worry about that a whole lot. And really, that's one I think that that transformation is a little easier for you all to get anyway, so that works out. All right, so let's see what this looks like. Now, I always try to space mine out in groups of 4 just because we know our key points are, in this one we're graphing sine, so it's x-intercept, max, x-intercept, min, x-intercept. So right now I have 5 spots for those 5 main points. Now I know it has to go through that cycle during my period, so from 0 to 4 pi. So I'm going to make my 4th mark 4 pi. And that way I have a spot for each of those key points. When we graph, we usually want to graph at least 2 periods, so I'll come out here. That's going to make that 8 pi. Now, if my 4th mark is 4 pi, what's the first mark? Yeah, that's going to be pi. I just take that period and divide by 4, and that tells you what your scale should be. Now, my amplitude is 2. Okay. And then remembering our sine graph and those key points that we just talked about, we have an x-intercept first. Then we have a maximum. So at pi, I'm going to go up to 2. Then at 2 pi, I have an x-intercept. Then I have a minimum, so that's going to go down to -2. And then I have an x-intercept again. And then I know that that pattern continues through one more cycle, so I'm just going to follow that pattern again. Now I'm just going to make a dotted graph here because this is not my final graph. Okay, this graph that I just made is for an amplitude of 2 and a period of 4 pi. I still have a horizontal shift of 2 pi. So what I'm going to do now is take my points from the amplitude and period change, and then I'm switching colors to green here, and my horizontal shift of 2 pi, I'm going to do that in green. So I need to shift right 2 pi because that's a positive. So now I need to look at my graph and how many spaces would 2 pi be? Well, one space is pi, so that second space is going to be 2 pi. So that tells me that I'm going to take everything and move it right 2 spaces. So this point comes right 2 spaces. I take my maximum and move it right 2 spaces. I take this intercept and move it right 2 spaces. I take my minimum and move it right 2 spaces. And I keep that pattern up. And now when I connect my points, this green graph is going to be my final graph. Okay, I don't quite have 2 pi here because, I don't quite have 2 periods here because I just have the one cycle here. There's one wavelength and then that's a half. That was terrible. There we go. That way it doesn't look so messy. So I can either extend it to the right or to the left either way. Okay, if I extend it to the left, I can tell that this, before my 2 pi, I'm going to have a minimum, and then I'm going to have an x-intercept here. So you can extend it that way, or if you want to make more spaces out here, you could extend it here. Okay, so now I actually have 2.5 periods graphed. Okay, but that's how you would graph there, and my green graph is the final graph. Okay, let's look at a cosine graph to make sure you know what to do there. On this example, we want to graph y equals -1/2 cosine of 2x. So once again, I need to find those key parts: the amplitude, the period, the horizontal shift, and the vertical shift. So my A value is -1/2, but if I take the absolute value of that, that's going to give me an amplitude of 1/2. So that means my maximum will be at 1/2 and my minimum will be at -1/2. Okay, period is 2 pi over B. Well, what's in the B spot this time? Yeah, 2. So my period is pi. Okay, do we have a horizontal shift? Nope, nothing is added inside of here in the parentheses with that 2x, and then nothing is added on the outside, so there's no vertical shift. So make my graph. Okay. This time, since my period is pi, I'm going to make the fourth mark pi, because once again, our key points for cosine, they start out with a maximum, an x-intercept, a minimum, an x-intercept, and a maximum. So I have 5 key parts. I have 5 spots to put those key points at now, because I have a point at 0, and then I have these 3, and I have a mark at pi. So if I go out 4 more, That'll get me to 2 pi. My amplitude is 1/2, so I'm just going to put a scale of 1/2 this time. Now, like we said before, our key points are max, x-intercept, min, x-intercept, and a max. Okay, that's the typical cosine graph. However, this time, look what we've got going on. That negative there, what does a negative in front do to a graph? Yeah, it flips it. So that just means my maximum is now going to be a minimum. Does it change your x-intercept? No, but what about your minimum? It's now going to be a maximum and then x-intercept and then min. Okay, so that's what's going to happen when I flip. So that flips or reflects across to x. And so this is what happens to your key points. Okay, so I graph my minimum at -1/2. I graph my x-intercept. I graph my maximum. I graph my x-intercept. And I graph my minimum. And I just follow that pattern again. And that's 2 periods. Okay. Now, why did we do everything just in one color, whereas on the sine graph we did 2 colors? On the sine graph, I did that second color to show you the horizontal shift. Because I think it's hard to change an amplitude and a period and a horizontal shift all on one graph. Okay, the amplitude and period are pretty easy to do together, and even the reflection, we did all of that on one step here. But since I didn't have a horizontal shift, I didn't see that it was necessary to be, because I don't have to move left or right there. If I had a horizontal or vertical shift, I'd probably do another color, and after I got these orange points, I would shift them however they needed to go and make a final graph. Now, I do want to make sure that you understand what this looks like in comparison to the real y equals cosine x graph. Okay. When we were graphing y equals cosine x, we started with a maximum, and actually that's not right, because we would start with a maximum up here at 1, and my minimum would be down here at -1, okay? And I know that I end in a maximum too. Right in the middle is a minimum, and then I have an x-intercept in the middle and an x-intercept here. So this black graph is my y equals cosine x graph. Okay, so do you see how different the orange one is? Not only does it not go up as high or as low, but it has 2 cycles during the time that this one just has 1. And then you can see the reflection piece too. Okay. Now, what would the regular sine graph look like for this last one? I'll graph it in black as well. Okay, the sine graph, our key points were x-intercept, and then a maximum, and then an x-intercept, and then a minimum, and then an x-intercept. And it did all of that between 0 and 2 pi. So this is kind of squeezed in graph here. That's the original sine graph. So do you see how different those transformations made the graph look? Okay, it really stretched it horizontally, and it stretched it vertically, and then it shifted it as well. Okay. Okay, hopefully that gives you enough good information to look at sine and cosine. The last thing I want to talk to you about are tangent and cotangent. I know this video is a little longer. I'll try to make the tangent and cotangent quick. But once again, I just want you to see what the shape looks like and understand why it does what it does. So when we're graphing, just switch back to draw, y equals tangent x. Okay, we need to pick some values for tangent again. I'm going to go back to using my pi over 4 increments. I'll show you why here in just a second. But if I look at 0 and then pi over 4, pi over 2, and then what's next? 3 pi over 4, and then pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. Okay, filling this t-chart out so we can get the shape of the basic graph. Okay. Remember, how do we find tangent on our unit circle? Yeah, tangent's y over x. So if you get out your unit circle, okay, think about what is the tangent of 0. Okay. Well, at 0, if I do y over x, I end up with 0. Okay, then at pi over 4, if I take y over x, those are the same, so I'm going to end up with 1. Then at pi over 2, if I take y over x, I end up with a 0 in the bottom. So that's going to be undefined. Then at 3 pi over 4, if I take y over x, I get negative 1. Then at pi, when I take y over x, I'm at 0. 5 pi over 4, y and x are the same, so I'm back at 1. 3 pi over 2, I have 0 in the denominator, so that's undefined. And then at 7 pi over 4, I'm back to negative 1. And then 2 pi should be the same as 0, so it's 0. Okay, make a graph again. And then I'm going to go and graph my points. Okay, so I graph the point 0, 0. And then at pi over 4, I have 1. At pi over 2, I'm undefined. Well, on a graph, when we have undefined, we usually have an asymptote. So there's an asymptote there. So it's usually an asymptote or a hole or something like that. So in this case, it's an asymptote. And then at 3 pi over 4, I have negative 1. Pi, I have 0. 5 pi over 4, I have 1. And then undefined again. So there's another asymptote. And then negative 1 and 0. Okay. Now, it's kind of hard to see at the beginning and the end of the graph what's going on, but here in the middle, in between those two asymptotes, what happens is you have a graph that looks like this. Does that remind you of anything? Kind of looks like the cubic function, doesn't it? Okay, it's not exactly the same as the cubic function because the cubic function doesn't have those asymptotes as boundaries. Okay, a cubic function can continue to get wider as you go, but this tangent function will not. Okay, so once I know that part, then I can go back at the beginning and put the one that goes up, and then this is the part on the other side. Now, I still have 2 periods graph because I have 2. When does this repeat? Okay, basically. So from here to here, that's going to be 1 period. Okay, and you can really see it on the t-chart because look what happens. There's my 0, and then where's the next 0? What's that difference? Pi. And then the same thing from pi to 2 pi's where I have another 0. That difference is pi. So 1 period is going to be pi. And on the graph, that just means you're going from pi over 2 to 3 pi over 2. That difference would be pi. Okay. Now this time, is there an amplitude? Nope, because you don't really have a maximum or minimum. Now that doesn't mean, though, that if you have a number in front of tangent, like say you have y equals 3 tangent x, is that going to change the graph? Okay, it's still going to be a vertical stretch, just like normal, but these are kind of hard to draw, so I'm not going to, you probably won't be real particular about that, but just know that tangent doesn't have an amplitude because there's not a maximum or minimum. Okay. Now, this period thing, let's talk about that a little more. It's different than what we saw in sine and cosine. Sine and cosine, and we won't really get into cosecant or secant, but they are the same. All 4 of those graphs have periods of 2 pi. And tangent is going to have a period of pi. And we'll look at cotangent here in a minute, and you'll see the same thing. It has a period of pi as well. Okay. So that's going to change things because now when we do our key points, we really just need our asymptotes. And then look what happens right in between your asymptotes. Right in the middle, we have an x-intercept. Okay. Are these points critical? Not really. I mean, we just put them on this first graph so that you'll know that in between those lines, it kind of makes that curve and it doesn't just shoot straight up it's not linear. Okay. If you were to add in pi over 6 and pi over 3, you would see the curve even more, but basically that's all those are for. So we don't really need those as much. We're going to focus on our key points as being the asymptote, the x-intercept, and then the asymptote again. Okay. Now, for tangent, how do you find these asymptotes? Okay, we're going to say our formula for that is going to be plus or minus the period over 2. And that's going to be before any kind of horizontal shift. Okay. So in this case, I have a period of pi. So that means I should have an asymptote at pi over 2 and negative pi over 2. Well, I don't have any negatives graphed, but could I figure out that there should be an asymptote there if I were to graph them? Well, if you went to negative pi over 2, that's going to be the second mark here. That would be negative pi over 2. Well, how many spaces do I have between these 2 asymptotes? There's 1, 2, 3, 4 spaces. So if I go 1, 2, 3, 4 spaces back, sure enough, I would have another asymptote there. And then I could finish my graph if I wanted to and make it go down that way. Okay. And then also negative pi over 2 is coterminal to 3 pi over 2. So it would be undefined, just like it is in the t-chart for 3 pi over 2. So we're going to graph the 2 asymptotes and figure out where those are by taking plus or minus the period over 2, and then stick the intercept right in the middle, which is what we did right here. Okay, let's look at cotangent. Now really, for this one, how are tangent and cotangent related? Yeah, they're reciprocal. So I can just take my t-chart that I made for tangent, and what can I do with all those numbers? Right, I can just flip them. So I'm not going to take into consideration the pi over 4s this time because we know those just made these little insignificant points here. Okay, we know that that makes the shape of the curve, but our key points are what we want to focus on. So those all happened at the pi over 2 increments. So when I make my t-chart for cotangent, I'm going to take 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so at 0, our tangent graph had a value of 0. So if I take 0 and find the reciprocal of that, that's going to be undefined. Okay, at pi over 2 for my tangent graph, I had 1. Reciprocal of that is still 1. At pi for the tangent graph, I had undefined. So this time, I'll have 0. Okay, and then at 3 pi over 2, what happens? Yeah, that's still negative 1. And at 2 pi, that's undefined again. I've messed something up here. What did I do? There's my mistake. Which was pi supposed to be? Actually, I got a lot of mistakes here, don't I? Erase all that there. I was looking at the pi over 4s instead. Okay, pi over 2 should actually be 0. Pi is undefined. And 3 pi over 2 is 0 again. Sorry about that. I was thinking 3 pi over 4 and then pi over 4. Can't read my own writing, I guess. Okay, so now we know that those undefined parts on the graph mean what? Yeah, those are going to be asymptotes. So I have an asymptote at 0. I have an asymptote at pi. And I have an asymptote at 2 pi. Now, what happens right in the middle? Pi over 2, an intercept. 3 pi over 2, an intercept. Now, I guess I probably should have included these, but let's say what would happen between 0 and pi over 2. So let's say at pi over 4. Okay, that's 1. So I'd have a point about here. And then what happens between pi over 2 and pi, or at 3 pi over 4? Yeah, that's going to be negative 1. So yeah, I probably shouldn't have left those points out. So that'd be here. Okay. All right, so the reason those are important is because now look at our shape. Still the same shape, but it's not increasing, is it? It's going to be decreasing. Okay. So that's one of the big differences with cotangent. Cotangent is going to be going down, tangent will go up. Okay. Now, could you make a cotangent graph that does go up? What happens if you put a negative in front of the equation? So if we were graphing y equals negative cotangent. Yeah, that's going to go up and it's going to look a lot like tangent. But do you see any other differences besides the fact that they are going in different directions? Look at where our asymptote is there. See how it's at pi over 2? Okay, we have his intercept at pi over 2. Our asymptote's at 0. Okay. So yeah, the direction is different, but then also the asymptotes and the intercepts are in different places. Okay, so right here, that's 1 period, which is pi. We can see that again on our t-chart. From here to here, it's undefined. That's a difference of pi. Same thing here, difference of pi. Okay, once again, no amplitude. But we know the graph decreases. Now, our key points. Once again, since it just has a period of pi instead of 2 pi, we can get by with 3 key points. We're going to have our asymptote, the x-intercept in the middle, and the asymptote again. Now, those key points, as far as the pattern, it looks the same as what we wrote down for tangent, but notice our asymptotes are in different spots. For tangent, we said to find those asymptotes, we're going to put it at plus or minus the period over 2. for cotangent, we're going to put those asymptotes at the beginning and end of the period. So that's why this one has an asymptote at 0 and then also one at pi. Okay, I think that's enough. Let's see how that goes. Message me if you have questions. Like I said, we actually did about 3 days worth of work. I just tried to do the bare minimum in these notes. I know they're kind of long, so I'm not going to get into any more details on tangent and cotangent. But congratulations, these are your last online notes. I don't know about you, but that makes me very happy. Have a great day. And like I said, just message me if you have questions. And also, it's your last official assignment for Precal. Congratulations, you made it. Even having a quarter of your year, or almost half actually, being super hard by doing this online stuff. You all have worked really hard, and I'm very proud of you for that, because if I'd known this was going to happen, I totally would have flipped it and done the trig first and the algebra second. But I guess we could